Hi everyone, my name is Jakub Klencki and I'm a PhD student at the Radboud University, working primarily with high elements, Arena Strat and nanopoles. And today I want to talk to you about the evolution of massive stars in interacting binary systems and the effect that may be played there by low metallicity. And so we know that most massive stars are formed in binaries or in triple high order systems even. And most of these massive stars will at some point strongly interact with their companions by transferring mass and angular momentum. And so usually this interaction happens as a result of expansion. A star expands during its evolution, and when it's in a binary, that leads to rush flow overflow and mass transfer. And so here I'm showing a radius versus age diagram of the evolution of a 25 solar mass star at solar metallicity, with the main evolutionary phases being shown here, the main sequence, the rapid phase of expansion, the Hertzsprung gap stage right after the main sequence, and then the core helium burning stage. And so we have two phases of expansion, main sequence, Hertzsprung gap. And so in a population of binaries, you would expect that for different initial masses of the star, and then depending on what the orbital period of the binary is, you would have a range of binaries with narrow, short periods where the interaction is started by a main sequence star, so a case A mass transfer, and then wider binaries where the mass transfer is initiated by a post-main sequence star, mainly a Hertzsprung gap giant, in this case of solar metallicity. But now this diagram could look quite a bit different when you go to lower metallicity. So now I added a dashed line here, which shows the radius evolution of a low metallicity model with the SMC composition. And what you see here is a halted expansion during the Hertzsprung gap phase. And so this star transitions to the core helium burning phase, while it's still relatively small. It's a blue supergiant here. And this type of radius evolution, post-main sequence radius evolution, is well known, found a long time ago in models of especially low metallicity massive stars. It is well known to be very uncertain and model sensitive to the internal mixing. We already heard even today talk from Avishai about the role of overshooting and semi-convection on the post-main sequence expansion of massive stars. But at the same time, this type of evolution at the low metallicity of Magellanic Clouds, for instance, seems to perhaps be favored because we do see a lot of blue and yellow supergiants in the Magellanic Clouds, which are presumably at the core helium burning stage here. Now, when we are talking about binaries, this way in which the radius expands is especially important. And so in the low metallicity, we might be getting this regime for the mass transfer interaction that is initiated by a star that is already at the core helium burning stage here, quite differently than at higher metallicity. So the goal of our research here is we want to understand what is the impact of this post-main sequence expansion and different types of donor stars on the mass transfer interaction itself, looking at three different metallicities, the solar composition, the LMC and the SMC compositions here. And what we do for this, we compute a grid of binary models with MESA, with positions shown here, covering the entire parameter space for the post-main sequence mass transfer interaction, including some case A mass transfer sequences as well. And now for simplicity here, we focus only on the donor star. We involve only the primaries, and the secondaries here are treated as the point mass that doesn't accrete any mass. So that's a big assumption to keep in mind. But let's jump into some results. So first, I want to show you an example from the middle of the grid where the donor star is initially a 25 solar mass star. In those models, the mass transfer starts when that star has a radius of around 90 solar radii in all the cases. I'll be showing three different metallicities in three different columns, and the top plots will show you the mass transfer rate, and the bottom panels will show you the envelope mass as a function of time in these donors. So let's see at the solar metallicity case here. Now there are different lines in the zoomed plots here corresponding to different initial mass ratios spanning a wide range. But as you can see, pretty much irrespective of the mass ratio, the mass transfer phase here is always a very short-lived phase of thermal timescale mass transfer reaching high mass transfer rates. And only after a few thousand years, the donor star is stripped of nearly entire envelope and becomes a hot, fully stripped star. So this is something that you sort of classically expect from this case B mass transfer evolution in massive binaries. But then when you go to lower metallicity models, we find something quite a bit different. So in most of these cases, the initial phase of rapid thermal timescale mass transfer slows down and the donor star regains thermal equilibrium, while it can still have a significant amount of mass left in the envelope here, a few solar masses. And in many cases, then the mass transfer continues on the nuclear timescale of core helium burning, all the way basically until the end of core helium burning here at the end of our simulations. In some cases, there could be a temporary partial detachment phases, which I'll comment about later. Now, in the few models with the most extreme mass ratio in blue here, the mass left in the envelope after the initial rapid mass transfer phase is especially small, around 2 solar masses, and these models actually detach for the rest of the core helium burning. But even then, in these models, they never become fully stripped of a hydrogen envelope. And so we can actually distinguish between the three main types of post-May sequence mass transfer evolution that we find in our grid, which will be shown here on the left. And on the right-hand side, I will show an HR diagram with the evolution of the donor stars in those binary models. So first we have, especially at solar metallicity, the evolution that has just the thermal timescale mass transfer interaction, leading to full envelope stripping. And the donor star, in such a case here on top, quickly contracts after detachment and becomes this hot, fully stripped star. Now at low metallicity, we get a lot of evolutionary sequences which are dominated by phases of nuclear timescale mass transfer when the interaction is very long and the envelope is not stripped nearly as fully as in the solar metallicity case. And the donor stars are typically these blue or yellow supergiants in the middle of the HR diagram, and they basically stay here in a similar location for most of the core helium burning in those mass transferring binaries. And we also find a third type, which is sort of in between, where we only have a short-lived rapid mass transfer in the beginning, this dashed line here, after which the binary detaches, but the star is only partially stripped. And as it contracts in an HR diagram, it never becomes this hot, fully stripped star, but rather lives in an area that's close to the main sequence or in the main sequence even. So now we can take a look at how these different types of evolution span across the grid of different masses and orbital periods that are computed. So again, the background colors here correspond to estimated evolutionary stages of the donor star at the point of rush loop overflow. And now the different rectangles indicating the models, I'm going to color according to what is the type of the mass transfer evolution that we find in those models. So we have models evolving through predominantly nuclear timescale mass transfer in this magenta color. We have blue colored rectangles, which correspond to models that experience this rapid thermal timescale mass transfer leading to full envelope stripping. And then we have the intermediate stage, the intermediate type of evolution with hatched rectangles, which correspond to quick mass transfer, but leading only to partial envelope stripping. And then we have some casing mass transfer as well. And so the big thing we realize here is that the parameter space for nuclear timescale mass transfer that we find at low metallicity models is roughly coincide with the mass range where the primaries or the massive stars at this low metallicity ignite helium as blue supergiants, and when they have this halted Hertzsprung gap expansion, as indicated by the background colors of core helium burning donors in these plots. And this is something that we anticipated. And somewhat surprisingly, we found that the nuclear timescale mass transfer, slow mass transfer evolution, also from models where the donor is still technically a rapidly expanding Hertzsprung gap star at the point of rush loop overflow, but still from the same mass range where the halted expansion happens. So basically, it seems that at low metallicities, it's possible that above a certain model-dependent mass, and the mass transfer interaction from post-May sequence stars may become dominated by this long nuclear timescale interactions and partial envelope stripping rather than full envelope stripping. And so obviously this will have consequences, for instance, for the formation of hot stripped stars by binaries. So here we're trying to estimate what would be roughly the fraction of primary stars, the more massive components of binaries, that will end up as hot stripped stars or Wolf-Rayet stars, depending on the mass and metallicity, as a result of binary interaction. So in the case of solar metallicity, this fraction is quite high, about 0.7. It doesn't depend on the mass too much, and comes from both the stars that are stripped in case A or case B mass transfer. But when we go to lower metallicities, we find in our models that this fraction that leads to stripped stars actually plunges after some mass here, 70-20 solar masses roughly. And this is because above these mass, we no longer get those hot stripped stars for case B mass transfer. We only really get them from systems that interact for case A and then case AB mass transfer and eventually become hot stripped stars. So much more narrow systems in general. So it does seem like perhaps above a certain mass, the binary formation scenario for stripped stars, for Wolf-Rayet stars, is not as efficient in low metallicity as you might think. Now, I should comment that the stars that are partially stripped in low metallicity models here, they may still become fully stripped by the core collapse. So from the point of the core helium depletion, when we finish the models until the core collapse, they are still mass transferring. But good question is whether the carbon-oxygen cores in these models are more reminiscent of single star or binary evolution products. Some food for thought there. Okay, one more thing I wanted to say has to do with the distribution of helium-burning stars in the HR diagram that we would roughly predict. So this is the case for the LMC metallicity. You see some single stellar tracks here, and there is a density map which will correspond to where you expect helium-burning stars in the HR diagram. In this case, just based on single tracks. So you have some red supergiants and some blue-yellow supergiants and the blue loops, or on the Houted expansion models with Houted expansion. But when you add binaries here now, well, only primary, but components of binaries, then you have core helium burning stars all over the place here, basically. And we can identify a few groups. So we get hot stripped stars here to the left of main sequence. In this mass range, we get them from both case A and case B mass transfer. In this higher mass range, we only get them from more narrow systems interacting on the main sequence initially. There's an interesting parameter space here of these yellow supergiants, which corresponds to this parameter space for predominantly nuclear timescale mass transfer. So if that was the case, then in that parameter space, we would expect a lot of the stars being in systems that are currently mass transferring, some wide eclipsing binaries, essentially. And then there is this parameter space here, which is populated by core helium burning stars that you don't normally get from single stars. And those are predominantly the partially stripped donors in detached binaries. So they are enriched in helium, nitrogen, many of which would probably be slow rotators, and very interesting stars. But of course, there's a question of what the companions to these stars are. Okay, so let me summarize by saying that the metallicity can have a big influence on the binary evolution of stars, depending on how they expand after the main sequence. And in particular, at low metallicity, we might have these donors that are not really fully stripped at all, but rather experience partial envelope stripping or even very long phases of nuclear timescale mass transfer. Thank you very much.